Okay. This morning I would like to conclude the calculation that I started yesterday that was due to the evaluation of the conductivity in case we consider a solid and we use the semi-classical equation of motion. The final equation that we obtained yesterday was that the gradient with respect to R of the out of equilibrium distribution function times the velocity plus the gradient of the out of equilibrium distribution function as a function of the wave vector times the derivative of the wave vector plus the partial derivative with respect to time, always of the out of equilibrium distribution function, is equal to the, let's say, contribution of the collisions to the evolution of the distribution function, that is f of r kt minus the equilibrium value r kt divided by the relaxation time. And yesterday I told you that if we make the assumption that the external field is uniform, so no position dependence of the external force, and is also constant, so we have not an explicit time dependence of the external perturbation, we may neglect both the term with the gradient with respect to the position and the partial derivative of the distribution function with respect to time. So a time dependence can be found, but that dependence is not due to an explicit dependence on time. And yesterday, I forgot to include one comment concerning the relaxation time. In this new version of the evaluation, in general, let's say, the value of the relaxation time is not set as it was for the Drude case, and for the Drude model, we had that the relaxation time was a fixed number whose value was always the same, irrespective of the energy of the electron, the wave vector of the electron. So that was the same for all the electrons. With the semi-classical, so in the approach using the semi-classical equations to solve the problem, one tries to allow the fact that the relaxation time depends on the wave vector of the electron. So somehow the dependence on the wave vector of the electron is similar to the dependence of the energy of the electron, as the wave vector and the energy are strictly connected with each other. So in principle here, I should write relaxation time as a function of K. So this is an additional degree of freedom that you give to the relaxation time to account for the fact that it may depend on the initial level, or in general on the level of the electron that is involved in the phenomenon of collisions. In principle, just to add a comment on this point, since I think that maybe we will not discuss that in detail anymore. So in principle, in this formalism, the relaxation time is not dependent on the distribution function of the electrons, since tau just depends on K, not on the equilibrium distribution function, nor on the out of equilibrium distribution function. But in general, if you think at the collision as a sort of interaction between the electron and something, then if you consider the electron before the collision and the electron after the collision may take, in those conditions, the collision may take place only if you have a final state for the electron. So in principle, if you start with an initial level for the electron, then after the collision you have a final level, that process can be observed only if the final level is empty. So to know if the final level is empty or not, you need to know the out of equilibrium distribution function. So in principle, a more detailed approach to the phenomenon of the collisions should in principle include also the contribution of the distribution function in the evaluation of a relaxation time, or at least of a probability to undergo a collision. But in this case, this feature, so the fact that you need to know whether the final state for the collision after the collision is free or not, is completely neglected. So you just, let's say, increase the level of detail, since you assume that now the relaxation time depends on the wave vector, but here you completely neglect the fact that, again, you do not know if the final state after the collision will be or will not be free. So for the moment, we keep this level of approximation, but in general, a higher detail of knowledge is required, and that detail requires the knowledge or the inclusion of the out of equilibrium distribution function in the evaluation of the relaxation time. But for the moment, let's keep just this wave vector dependence here in the equation. At this point, since we know we have a relation between f, the out of equilibrium distribution function, and the contribution of the external forces that is here, we may write down an expression for f. We were trying to find a closed expression for f. So we start from this expression, rkt times k prime is equal to minus the difference between the out of equilibrium distribution and the equilibrium distribution. And if we call, just for an additional comment, if we call this delta, and delta if out of equilibrium function minus equilibrium function, you may write down f to be equal to, for the moment, since I suppress the coordinate dependence, just to concentrate on what I'm going to say. So here you have that f is equal to f0 plus delta. So in this equation, if we rewrite this equation considering delta, we have that the gradient with respect to k of f0 plus delta times k prime is equal to minus delta divided by the relaxation time. So if you notice here, you have delta on the right side, but you also have delta on the left side. You have delta within the gradient. At this point, one assumes that in general, the deviation from the deviation of the out of equilibrium distribution function with respect to the equilibrium one is small. So if you keep the calculation at the first level of approximation, here you have that this term here, that is the deviation from equilibrium, is proportional to the gradient of the equilibrium distribution function plus the deviation from equilibrium. So what you expect is that if the deviation from equilibrium is small, this term here may be approximated just with the equilibrium term. So you suppress this the contribution of the small deviation from an equilibrium from the gradient, as if you assume that the deviation from equilibrium is small, the derivative of that with respect to the wave vector is expected to be even smaller. And so you suppress delta here and you keep just delta on the other side. So in this way, you have a closed expression for delta, because here you have delta just on one side, you have not delta within the gradient operator, because otherwise the problem will be more and more complex, since you have to solve a differential equation where the variable is delta. So in this case, due to simplify the calculation and assuming again that the deviation is small, you just keep this final expression for the for delta. So thanks to that, we may find an expression for the out of equilibrium distribution function. So f of r k. Just a moment. There's a bell ringing. I just wait. Yeah, just a moment. Sì, poi. Okay.
Prof?
Sì?
Sì, di solito succede con le porte di emergenza quando vengono aperte per sbaglio.
Ah, ok, perfetto. Sì, no, infatti Giusy ha detto che è tutto a posto.
Ok, ok.
Grazie.
Niente.
Okay, so the final expression for f can be obtained by the grid tau relaxation time. Just wait. No. Okay, so starting from this, from this equation, we have that f of r k t is equal to f0 of r k t, and then we have the gradient of k of f0 r k t times k prime times the relaxation time. And here we have a minus sign. So at this point, using this expression, we may evaluate the integral that we have already evaluated in the past for the calculation of the density current. And in this case, just to include the fact that, let's say, we need to insert into the equation the contribution of the external field. The contribution of the external field can be injected into this expression by using the fact that here we have a k prime. If just a uniform constant field is applied, we know that the semi-classical equation is that h bar k prime is equal to minus c times the electric field. So in place of this k prime, we may write down minus c times e times h bar. So the new expression for this is f0 r k t. Then we have plus the gradient of the equilibrium distribution function with respect to the wave vector. Then we have E electronic charge times the electric field divided by h bar times the relaxation time. Okay, from now on, due to the fact that we have no contributions that change from position, depending on the position, I will suppress the r coordinate in the distribution function, and I will always also suppress the explicit time dependence, since in this case we have no energy or contribution that depends explicitly on time. So from now on, I will just write down f of k or f of e, depending on the variable of integration. So the expression for the density current is minus e, then we have the volume element divided by 2 pi to the power of 3. Here, In the density of level, we have the volume, but the volume is then simplified when we want to obtain not just the number of electrons, but the density of electrons. Then we have a two-factor, and the two-factor is due to the fact that one level may host 2 electrons. Then we have an expression for the out of equilibrium distribution function times the velocity, that is 1 divided by h bar gradient with respect to k of the energy. And in this integral, we may, and this integral is performed over the first Brillouin zone. So here we have minus e, then the integral of d3k with respect to 4 pi to the power of 3, then f is equal to f0 of k plus the gradient with respect to k of f0. Then I have electronic charge electric field divided by the reduced Planck constant relaxation time times the velocity. As this, if we may split this integral into two parts, one with f0 and the other one with the gradient. The part with f0 gives a contribution that is equal to 0, since at the equilibrium we have an even occupation of the levels. So this function here is an even function of the coordinate. The gradient is an uneven function of the coordinate, so the volume integral will be 0. That is just an indication of the fact that if you have no external forces, then you expect that the average current that is transported by the material is equal to 0. So you have an average velocity of the electrons that is equal to 0, as you are again in equilibrium. So from now on, I will just consider the contribution of the gradient. Okay. So just rewriting that, J is minus C. Please check if I'm missing some constants. Then I write here that there is the E, the electronic charge that comes from the external force. Then I have here divided by h bar squared, and one h bar comes from the derivative of k prime, and the other h bar comes from the definition of the velocity. Then I have the integral over the first Brillouin zone of d3k divided by 4 pi to the power of 3. And then I have the gradient with respect to k of f0. And then I have the gradient, here I have a scalar product with the electric field, and then I have the gradient of the energy with respect to k. And if we consider the relaxation time, if we consider this gradient, here we have the gradient of the distribution function with respect to k. The dependence of k on k in the distribution function is just through the energy. So we may rewrite the gradient of f0 as a derivative of f with respect to the energy times the gradient of the energy with respect to the wave vector. So we may replace this expression here. And if you look at this, this is the derivative of the distribution function with respect to the energy. In general, and this is the derivative of the equilibrium distribution function. In general, if we suppose to be at low temperature, so I use EF here and not the chemical potential, the equilibrium distribution function is just it's just like this. So 1 here, 0 here, and the only variation that you may observe is close to EF. So from the point of view of the calculation, this derivative of F0 with respect to the energy is just like, let's say, not a Dirac delta, but is a function that is 0 everywhere apart from this small range of energies, or the equivalent range of wave vectors. Due to this fact, since at the moment we do not know what is the dependence on the relaxation time on the wave vector, we may replace this expression, that is the relaxation time, as a function of k. So, but we at the moment don't know what is the actual dependence of the relaxation time on the wave vector. We may replace this by relaxation time evaluated at EF. And this can be done due to the fact that, again, the derivative of 0 with respect to the energy is a function that is different from 0 only in a small range of energies or a small range of wave vectors close to EF. So due to that, I may I may neglect the actual dependence of relaxation time on the wave vector and just include here one specific value of the relaxation time. So due to this variation, we have that this is equal to minus E squared divided by H bar squared. Then I have relaxation time evaluated at EF, integral over the first Brillouin zone of the volume element. Then I have the derivative of F0 with respect to the energy times the gradient of the energy with respect to the wave vector, scalar product E. Then I have the gradient of the energy, again, with respect to K. Here we have, let's say, the classical expression, the typical expression that we have already seen, always seen, relating the density current and the electric field is an expression that is like this one here. So you have that the density current is sigma, where sigma is the conductivity applied to the electric field. In this case, the application of sigma is not just the multiplication, is not just a product by a constant coefficient, because here we have to consider the fact that the gradient, we have this scalar product with the gradient and the electric field, and then we also multiply again by the gradient of the energy. So we can rewrite, considering the components at this point. So at this point, we may consider J as it is, as a vector. So if we consider just one component that I label using alpha, then that is equal to minus E squared divided by H bar squared, relaxation time, integral over the first Brillouin zone. Then I have the derivative of F0 with respect to the energy. Then here I have the partial derivative of the energy with respect to so, and here, let's say I do not write explicitly that, but since we have two indexes that are repeated, there is a summation over that index. So at this point, we may rewrite this as J of alpha is equal to sigma alpha beta E of beta. So at this point, the conductivity is no more, let's say, a coefficient, a constant term, but can be seen as a tensor. And at this point, we may focus on the evaluation of just this contribution Yeah. So to, let's say, find the closed expression for sigma, we may consider this part of the integral, and we may we may perform the integration by parts. So if we consider this expression, so the derivative of, with respect to k beta, of G0 times the derivative of the energy with respect to k alpha. So in this case, that is equal to the derivative. When we apply the derivative to, sorry, not G, this is F. When we apply the derivative with respect to k to F, then we have the derivative of F0 with respect to the energy times the derivative of the energy with respect to k beta. So this is the derivative of the first term. And then we have F0 times the second derivative of E with respect to k beta, k alpha. So this is what we have in the integral. So we may replace that by the summation of this term, the term that we have here, minus the term that we have down here. Okay, I just now switch to a new page. So sigma alpha beta is equal to minus E squared divided by H bar squared. So here we have the derivative with respect to k beta of F0 times the derivative of the energy with respect to k alpha minus F0 second derivative of the energy with respect to k beta, k alpha. Now, if you notice the first term gives you the, let's say, gives you the sum of the three partial derivatives of this contribution with respect to the same variable. So this is the divergence. At the end, what you have is that you have the divergency of something if you consider the integral just with this term. So the integral over a volume of the divergency of something is the integral over the surface of that volume of what you have within the parentheses. So in this case, this is transformed over an integral over the surface of the first Brillouin zone of the surface element, and then you have F0 times the derivative of the energy with respect to k alpha. So this F0 in general is an even function of the energy. So as the symmetry of the symmetry of the energy function follows the symmetry of the Brillouin zone, then you have that F0 will have on opposite points on the Fermi surface will have the same value. But if you consider this here, the derivative of the energy is an even function of k, so the derivative of the energy is an uneven function of k. So you have the integral over the surface of the first Brillouin zone of the product of an even function times an uneven function. So what you expect is that this integral will be equal to 0. So the only part that survives in this integral here is the second. So this can be kept for the evaluation of the conductivity. The minus sign here is, let's say here you have one minus, another minus, so you just have a plus sign at the end. So you have E squared relaxation time divided by H bar squared integral over the first Brillouin zone of the volume element. Then we have F0 times the second derivative of the energy with respect to K beta, K alpha. If you take the second power of the reduced plus Planck constant and you keep that into the integral, you have that 1 divided by h bar squared times the second derivative of the energy with respect to K beta, K alpha is the inverse mass tensor. So this is equal to E squared relaxation time integral over the first Brillouin zone or let's say the inverse mass tensor is based on the Hessian on the energy, so alpha beta or beta alpha is the same because that is symmetric. So you have this new expression, new with respect to the case of Drude and the case of Sommerfeld, expression for the conductivity. And in this case, the conductivity, again, is no more a coefficient, just a constant term, but is an actual tensor. And that is related to the value of the effective mass of the inverse of the mass tensor. In case, so this is the general expression that is always fine. But in case we are considering a region of the electronic band structure where m to the minus 1 is equal to one divided by m star times identity. So we are not exactly in a free electron situation, but the effective mass, the inverse of the mass tensor is diagonal. So you have just elements on the diagonal of the tensor, and the three elements of the over the diagonal are exactly the same. So in this very simplified situation, we have that sigma alpha beta is E squared relaxation time. Then we have effective mass at the denominator, and then we have the integral over the first Brillouin zone of F0 times the volume element and the identity. So as the identity is not part of the integral, we may just, at this point, we may evaluate this integral, and this integral gives us just the electronic density over the first Brillouin zone. So this can be written as n E squared relaxation time divided by m star, and then we have the identity. So we have a tensor where that is diagonal, as it was the inverse mass tensor, and the three elements on the diagonal are the same. So in this case, the system is isotropic. So here we have, we made the assumption that the system is isotropic. So what we find is a conductivity that is isotropic for the same motivation, and this expression is again the expression that was found by Drude and Sommerfeld. Now, as it happened yesterday for the Hall coefficient, we have the opportunity to include here not the value of the electronic density that was evaluated by Drude, so fixed from the beginning by choosing the value of Z, the number of electrons that each ion shares with the solid for the metallic bonding. But here we have the actual density that comes from the evaluation of this integral. So this may be smaller than the Drude value. In addition, here at the denominator, we have the an effective mass value for the electron. So also in this case, if the motivation, let's say, the point is always the same. So in case we have a point of the electronic band structure where the band structure of the solid we are considering is symmetric, or as the same behavior, is isotropic, sorry, and in particular is quadratic, then in that case we may again go back to the free electron picture just by redefining the value of the effective mass of the electron. So also in this case, again, the expression for the conductivity is always the same, but what changes is in particular the value of the effective mass and of the electronic density. So this result is one of the motivations behind the fact that when I started the classes, the lessons, I told you that in some situations, even if you use the simplest model, you may find some results that are in agreement with those that are found by the more complicated models. So in this case, the structure of the conductivity is always the same. You may just redefine some quantities, and then with this recalibration of the mass and of the density, then everything is fine and is in agreement with what you expect to find for that system. So even in situations, again, you need a specific situation, since you need a system that is isotropic and also has an overall quadratic dependence of the energy with respect to the wave vector. But so this is quite a peculiar situation. But due to the fact that you may actually find cases where this situation, this requirement is met, then in that case, just a rescale of the coefficients can be fine for the description of the properties of the system. Okay, and if you have no questions, do you have questions or comments regarding this part here? Okay. Now, just before the break, I would like to introduce the last point of this part regarding the contribution of these semi-classical equations, or in general, this description of the effect of the external field on block electrons. And this part is related to an effect that was observed experimentally in the lab when they try to apply a magnetic field to a system and to measure how some parameters, for instance, the magnetic susceptibility, changed depending on the value of the external field, of the external magnetic field. So here, again, we assume that we are applying to the system a value of B that is, as in general, is then applied along a specific direction. And this, in this case, the magnetic field is constant, so it doesn't change with time and is uniform over the sample volume. What was done during the experiment was to evaluate the dependence, for instance, of the magnetic susceptibility as a function of the external field, as a function of B. Since it's easier to display the result when you, on the horizontal axis, do not plot B, but plot 1 divided by B, I make this drawing here by using as an x variable 1 divided by B. What they saw was that if you plotted the susceptibility, for instance, as a function of 1 divided by B, the dependence was like this. So what they found was a periodical dependence of the macroscopic parameter as a function of 1 divided by B. In some situations, they found something that was even stranger, because they found that for some solids, you have a double periodicity. So you have a short scale periodicity here that is superimposed to a long scale periodicity. So the idea was to explain why that effect was observed. So the question was, why does a parameter as the susceptibility, but also other parameters display the same behavior, has this dependence of 1 over B? And due to the name of those who performed the experiment, the effect, this particular peculiar effect, oops, was observed through an experiment to a configuration that was introduced by de Haas and Van Alphen. And I just make an introduction, then in the second part of the lesson I make all the calculations. The idea here is that this effect was studied and investigated first by Landau for free electrons, then Onsager applied the results of Landau also to the case of Bloch electrons. So the starting point of the theory that tried to explain this effect was to evaluate what happens to the electronic levels when you consider the application of an external field. And the first approach was based on the free electron picture. As you've seen in a while, the free electron picture was the easiest one for what concerns the calculations that had to be performed for to find what happens to the electronic level. And I anticipate you something. Why do I present you this kind of effect? I present this as, let's say, when we consider the nearly free electron approach, tight binding model, orthogonalized plane wave model. So we use many different approaches to try to find indications concerning the electronic band structure of the electrons. But this is an approach that is theoretical. So you use a model to describe your solid, and according to that model, you find an energy versus wave vector dependence for the specific situation you are investigating. So we have seen many different models that try to predict what is the actual energy versus wave vector dependence in case you consider your system. Then once you have those results, you need to compare those results with something. So if you, as I show you when I displayed the different shapes of the Fermi surfaces, if you have a model that predicts that, then you need something to compare with your model to check whether the conclusions of the models are fine or not. It turned out that when the model for the explanation of the de Haas-Van Alphen effect was completed, then the explanation of this effect went through an actual measure or an actual probe of the Fermi surface. So through the explanation of this effect, it's possible to obtain indications concerning, let's say, not exactly the shape of the Fermi surface, but to have indications concerning the extension in the three-dimensional reciprocal space of the Fermi surface. So we will see that at the end of the calculations, some details concerning the Fermi surface can be obtained. So this is one effect that, if explained, can give us some details concerning the shape, the structure, and the evolution in space of the Fermi surface. So is performing an experiment using the Husband-Alfvén configuration on a system allows us to extract details concerning actually the Fermi surface. And the starting point of the calculation for the free electron case was to solve the Hamiltonian when we consider the Hamiltonian for the electrons, that includes the contribution of the external field. And in this case, the Hamiltonian has this structure. So A is the vector potential associated to the magnetic field B. Q is the charge we consider. In this case, Q is minus E, so is the charge of one electron. And just to fix the expression for A, if we evaluate this curl, we have that we have to write down something here so that the derivative of the application of the curl gives us a vector that is 0, 0, beta, 0, 0, b, sorry. And in this case, the gauge that is used is minus b times y 0, 0. So if you apply the curl to a that has this structure minus b times y 0, 0, then what you find is that the actual value of b is 0, 0, b as we need for this experiment. So at this point, what is done is to rewrite this parenthesis, including this expression for A. And please, I just had a comment concerning this hat that I put over the symbols. In the following, I will have let's say, I will use the same symbol both for the operator and for the result of the application of that operator to a wave function. So I will call, if I apply P to a wave function, I will call P the result of the application, but without the hat. So I put the hat to distinguish the operator from the result of the application of the operator itself. So when I put hat, that means the operator P. When I just write P, that means the value that results from the application of P to the wave function. So here we have 1 divided by 2m. Then we have px operator. Then we have minus b y operator. Then we have the multiplication by the charge that is minus c. So here we have a we have 3 minus, 1 minus here, 1 minus due to the charge, and 1 minus due to the vector potential. So at the end, we have a minus here with the electronic charge. Then we have py operator squared plus pz operator squared. So this is the expression for the Hamiltonian in case we consider an external field B with this symmetry, so B parallel to Z, constant and uniform. And what we will do after the break is to apply this Hamiltonian to the wave function of the electron and to try to solve the sorry. So we will try to evaluate E and also to have some indications concerning the wave function. Okay, so this was just an introduction, and as the calculation, let's say, is not so long, but maybe it's better to do that after the break. Then I stop here for a while, and then I go on with the second part after the break. Do you have questions or comments regarding this point? Okay, so stop